There it was. You gotta love it. All right, guys, so here's the scoop. Today we get to start talking about the so whats. So in the last homework assignment, we just identified what molecules are polar. We talked about the directions of their polarities. You drew in the arrows. And then, guys, in question number 16, we also identified the idea that not all polar bonds have the same polarity. Well, guys, today what we're going to do is we're going to start talking about the so whats. What does that matter that these molecules are or aren't polar? And even if they are polar, they don't have the same polarities. And guys, along the way, we're going to talk about what are called intermolecular forces. And then this is going to lead to a conversation about physical properties. And then we're going to do a deeper dive on that on Tuesday when we go to lab. Groovy? All right. Yep, so we are doing a lab on Tuesday. So guys, let me set the stage for you. Don't write any of this down. But here's where we are right now. So guys, last time we learned about polar covalent bonds, and we learned that if these molecules are not symmetrical, that leads to polar molecules, and we represent these polarities using arrows. Can I get an amen? All right, now, guys, what we're going to do with this today is we're going to take these ideas and we're going to look at how these polar molecules behave when they get in big groups. That's our goal for today. So yeah, we get that some molecules are polar and some aren't, but what do these things do when they get together? And guys, to understand the answer to that, you need to understand something called, see it up here, intermolecular forces. That's actually a part of your notes. Scratch it down. It's not a sub, it's actually the first important idea in your notes. All right, so guys, what are intermolecular forces? Well, guys, the story goes like this. Polar molecules, right, the polar ones, the ones that get the arrows, polar molecules, when they gather together in large groups, are actually attracted to each other. So guys, let's talk really quickly about attraction. These magnets are crazy. So guys, the idea is this. You understand with magnets, right, that magnets have got a north pole and they've got a south pole. These are actually strong enough they'll attract through my hand. Oh, it's flipping over. This can't be good. Oh, what's going to happen? Okay, there we go. So, guys, you understand that they've got a north pole and they've got a south pole, right? So if this magnet is north pole up, what do you know about the magnet underneath? Which way is its north pole pointing? Also up, because they attract north pole to south pole. So we've got the south pole down here, the north pole up here, and that attracts, right? And so we understand that magnets attract pole to pole, north to south, right? Well, guess what? So do polar molecules. But instead of being north to south, they attract positive dipole to negative dipole. See the connection? No pun intended. So the idea here, guys, is that magnets attract north pole to south pole. These polar molecules attract positive dipole to negative dipole. So the positive dipole from one molecule attracts the negative dipole from a neighboring molecule, and vice versa, and they just stack up upon one another. So guys, understand these forces of attraction between these molecules, these are not magnetic forces. They have a different name. These forces are actually what are called intermolecular forces. And guys, feel free to abbreviate IMFs. This is a universal abbreviation. The AP graders will allow you to use it if you come back for AP next year. This one always works. So here's what we know. Polar molecules, they have positive and negative dipoles. We represent them with arrows. And guys, these positive and negative dipoles in these molecules actually attract each other. And when they do, they create forces that we call intermolecular forces, or IMFs. You guys good to there? You're writing. I can't get over how strong these magnets are. Did I show you my really scary magnets? I'll show them to you when we're done with this. They are terrifying. Like, I'm going to throw them out because they scare me. Oh yeah, they fly apart. Oh yeah, it's like you can feel the force. No. I doubt it, but these ones can. Like, yeah, okay, I'm weird, right? It'll go through my calf. Like these ones will. You're wondering how I knew that. I'm like, I wonder if it'll go through my, well, and that's the thing, is it was attracting, and then it, like if this was my calf and it was those bigger magnets, they slid over, and then they pinched me, and I just about passed out. Yeah, it was horrible. It was not good. All right, now I got to show you these magnets. Yeah, we have time. So, yeah, right. Okay. Yeah, hold on. Yeah, so, I mean, seriously, you can't get these apart. Like, oh, no. Yeah, these things are horrible. Like, I seriously, you can't get them to budge. I ended up having to take a putty knife, and like they're not, all right, I give up. I'm just gonna go stick these back to the board. I hate those, they make me angry. Like, they're just horrible. They're like devil magnets. I don't like those things. Yeah, what? I know, right? Like, but the problem is you can't get them apart again, so they only spark once and then you're done. Yeah, they're horrible. I just hate them. I don't know why, they just make me, Maurer bought them for me. And they're, yeah, he's like, we need magnets because we're always talking about forces. I'm like, great, buy us magnets. And he bought those. Good heavens. All right, so guys, you get the idea here? Forces of attraction, intermolecular forces, right? Okay, so now the next thing you need to understand about these IMFs is that they're relatively weak. Guys, they're only about 1/10 or 100th the strength of a covalent bond. But guys, the thing that's interesting about them is they don't all have the same strength. Not all intermolecular forces have the same strength. But guys, this is not that foreign of a concept. You ready? Here's the idea. These magnets are stuck together really hard, right? These magnets still stick together pretty well, but, oh, it broke. But I can still pry them apart. Yeah, it chipped. But then, guys, I've got these little wimpy magnets, and they barely stick together, right? So you don't have a problem with the idea that not all magnets stick together with the same strength. Well, guess what? Not all polar molecules stick together with the same strength. Some of them stick really hard. Some of them stick together more weakly. So what is it that determines how strong the intermolecular forces are? And the answer is the polarity of the molecule. The more polar a molecule is, the stronger its intermolecular forces. So guys, the question then becomes this. How do we know how polar a molecule is going to be? The answer is question 16 from the homework. Remember what you did in question 16 in the homework where you stacked up the bonds in order of polarity? That's why I had you do question 16. Because the more polar the bond, the more polar the molecule. The more polar the molecule, the stronger the intermolecular force. So guys, we're going to come back to the logic of question 16 in just a minute when we start looking at real life examples. But the idea is this: in order to know how polar a molecule is, you've got to subtract their electronegativities. The bigger the difference, the more polar the bond, the more polar the molecule. We'll talk more in a minute. Okay, so guys, this is how we're going to handle this. And I don't even think you need to write this down. Just hear this. Guys, we are going to get really good today in talking about cause and effect reasoning. Are you guys familiar with the idea? Okay, so guys, if you are thinking and if you are presenting an argument in a cause and effect way, what word will you use as you're presenting your argument? No, not. It's better than because. Think about the book of Romans and the Apostle Paul. Did you say it? What word shows up all over the book of Romans because Paul's making arguments? Almost every chapter begins with this word. Therefore, or thus. Yeah, depending on the translation, it's thus or therefore. And Paul's always doing it. This, therefore that, therefore this, therefore that. He's creating arguments. Well, guys, we're going to do the same thing. And you don't need to write this down, just understand, we're going to use the word therefore a lot. But guys, here's the cool thing. You guys know there's a mathematical symbol for the word therefore, so we don't have to write it down? Do any of you know it? It's actually 3 dots in a triangle. Did you know that? Yeah. So guys, when you use the word therefore in this class, you can use the triple dot triangle. They'll let you do this on the AP test too. So when you're developing your arguments, as you want to use the word therefore, you can actually use the triple dot. You're going to love it. All right, you guys ready to go? That's the background, intermolecular forces. You good? All right. So guys, what are we going to do with this? This is where you need to start taking notes again. So guys, here's our laundry list for today. You ready? The idea is this. The strength of the intermolecular forces within a substance has everything to do with how that substance behaves. And guys, that's what we're going to do today. We are going to tie intermolecular forces to behaviors. So the question then becomes, what behaviors are we going to talk about today? Well, guys, you're going to find out that there are kind of like 4 or 5, depending on how you chunk this together. So guys, what I'm going to do is I'm going to show you all of the behaviors that we're going to talk about today. Now, some of them are going to be foreign to you, and you're going to want to define them, and I'll give you the definitions. But then we'll come back to them and apply this as we go. So guys, the first behavior that we're going to talk about is phase. Do you guys know the 3 phases of matter? Solid, liquid, and gas, right? So guys, what is it that determines if a substance is a solid, a liquid, or a gas? And the answer is the strength of the intermolecular forces within the substance. And guys, what is it that determines the strength of the intermolecular forces within the substance? The polarity of the molecules. Can you see how this is going to become an argument that you're developing? This molecule is polar, therefore its IMFs are strong, therefore this is true. So we're going to dig into it. Yeah?
So does temperature affect polarity?
Oh, that's the lab we're doing Tuesday. It does, no. What do I say without giving away the lab? It doesn't affect polarity, but it does affect the strength of the IMFs. You'll see. That's a great question. So guys, number 2. Well, actually not quite. So guys, once we figure out how IMF strength relates to phase, we're then going to focus only on liquids. And there are 3 properties of liquids that you're going to be asked to understand. The first is what is called volatility. So what does it mean if a liquid is really volatile? What it means is it evaporates really easily. Let's make this shorter. We can do better than that. Oh, not all caps. How about that? That's easier. So guys, volatility we are going to define as the ability of a liquid to evaporate. So some liquids evaporate really easily. They're said to be volatile. Some liquids, like oil, you spill oil and it will not evaporate, or it evaporates really slowly. So guys, that's volatility. Then guys, the next is boiling point. Boiling point is the temperature at which the molecules in a liquid have enough energy to turn into a gas. And then guys, we've got two more. We're going to kind of lump them together at the end of the day, but we'll separate them now so you know the definition of each. The next one that we're going to talk about is what is called cohesion. Cohesion is defined as the attractive forces within a substance. And then cohesion's twin, if you will, is adhesion, which is the attractive forces that exist between two different substances. So guys, that's our laundry list for today. We are going to figure out the polarities of some molecules. Once we know their polarities, we're going to talk about their intermolecular forces. Once we know their intermolecular forces, we're going to figure out whether they're solids, liquids, or gases. If they're liquids, we're going to figure out if they have higher low volatilities, higher low boiling points, and higher low adhesive and cohesive forces. This pretty much lays out the rest of the day for us. You ready to move on? You okay? You all caught up? You're good? Okay. So guys, in order to have this conversation, the first thing we've got to do is we've got to find some real life examples. So guys, the next thing you want to do in your notes is write down these three examples, spread them out the width of your paper. Like put CH3OH right in the middle, and then center CH4 in the space to the left, and then center H2O in the space to the right. Then guys, what we're going to do is we're going to draw their Lewis dot structures, but you've already drawn all of these, so I'm just going to give them to you. Make them fairly big, like an inch square, if you will. So that's CH4. But guys, once you've written it down, picture it in your brain. Can you picture what this looks like? Whether you know the name or not, guys, you need to be picturing that this, and you don't need to draw this, but you need to be picturing that this thing's a tetrahedron, right? Okay. We'll talk more about that in a second. So now, guys, what we're going to do is we're actually going to go to the far right. Let's do the other one that's really familiar to us, and that would be H2O, which is water. So let's draw, and guys, you're going to want to draw it just, you know, it doesn't have to be like this, but you may as well make it like this so that we're all doing things similarly as we start doctoring up these diagrams. But guys, when you picture then water in your head, you should be picturing something that looks like this, that we've represented like that. Does that ring true with you? Okay, now guys, CH3OH. You've actually done this before, but guys, it looks like this. This is what a CH3OH molecule looks like. We're going to draw the Lewis dot structure like this. And I would encourage you to draw it like that. And then guys, we understand that three-dimensionally, it looks like this. So I have a question for you. Why did I have you do water first? And why did I have you draw CH3OH just like this? Do you see the connection? Guys, check this out. Look at what we've got. We've got a hydrogen going to an oxygen going to something. We've got a hydrogen going to an oxygen going to a different something. So guys, the only difference between water and CH3, I don't know if I can do this. The only difference between water and CH3OH is what's hanging out over here. This is a hydrogen, this is a carbon and 3 hydrogens, but the structure of these, can you see it, is largely the same. That's going to be important in a minute. Okay, so guys, you got your Lewis dot structures drawn? Now let's talk polarity. So guys, let's go back to CH4 and let's start drawing in our polarity arrows. So guys, what direction does the polarity arrow go in CH4? It doesn't. Why? It's good. It's symmetrical and therefore nonpolar. So guys, you can probably just write that directly below yours, right? Just write nonpolar. You know what? I'm going to move that. I've been working on these notes like feverishly for the last couple days. I'm still tweaking them though. You guys are the first people to see them in that form. Is that, that's okay, right? Even though it's over the draw, is that, we're okay? Okay. So guys, now we need to draw in the polarity arrows for these other molecules. So let's talk. Let's start with water. Is water symmetrical? Is water symmetrical? No, but can we talk about this? Relative to question 19 in the homework, what is it that makes water not symmetrical? The unbonded pair of electrons. Remember, guys, we talked about the idea that unbonded electrons bend? And so, guys, water is not symmetrical because of these unbonded pairs of electrons. So now what do we have to do to figure out the polarity of the molecule? What do we need to know? Electronegativities of the atoms. Guys, look what I did for you. I looked them up already. So now, guys, let's draw in our polarity arrows. So here we go. So looking at water, we'll do water first. This bar right here, does the arrow point towards the oxygen or the hydrogen? This is your homework from last time, right? That points towards the oxygen. What about the other bond? Also points towards the oxygen. So now that we've established that, guys, what direction does the overall arrow point? Up to the right? Like that? Is that okay? All right. Now, guys, let's do the same thing with CH3OH. This gets a little bit more complicated. So, guys, looking at these bonds over here between the hydrogens and the carbon. Hydrogen is 2.2, carbon is 2.55. Which direction does this bond point? Towards the carbon or hydrogen? Carbon. So this goes this way. So does this one. So does this one. They are all carbon-hydrogen bonds. They all go towards the carbon, just like the homework, right? Is this all right? Okay. Now, guys, what about the bond between the carbon and the oxygen? Towards the oxygen, because the oxygen is stronger. And now, guys, what about the hydrogen to the oxygen? Just like this one went up, this one goes up in that direction. Now, guys, what direction's the arrow gonna go? So let's look. We've got all of this closing in here, and then we've got this coming up. So we've got that. Would you buy that? That this is moving like this is moving like this, and the net result would also be that. You guys good on that one? Okay. Now, guys, something new. And this is going to be initially tricky for you, but you're going to be doing this in homework, so let's talk. Now what we're going to do is we're going to put these molecules in order by increasing polarity. So we're going to go from the least polar molecule to the most polar molecule. So guys, let's pick the easy fruit first. Which one of these is the least polar? The one on the left, the one that's non-polar. So guys, next to that, you're going to want to write down least polar. All right, now we got to talk. Water and CH3OH. Guys, these are both polar, but which one is more polar? Here's the answer. The molecule with the most polar bonds will be the most polar molecule. And guys, this is like question number 16 in the homework. So it goes like this. We're going to do some subtraction. So guys, 3.4 minus 2.2 is basically 1.2. So that bond has a polarity of like 1.2. Guys, what's the polarity of this bond? Also 1.2. What's the polarity of this bond? Also 1.2. So far it's completely a tie. But now, guys, let's go up here, and what's the polarity of this bond between carbon and oxygen about? About 0.9-ish? And typically you can estimate. So guys, look what we just found out. This molecule, where it's polar, where this molecule is polar, this bond is a little bit less polar than all the other bonds. So if this bond is a little less polar, that makes this molecule a little less polar. Does that make sense? So here's what we now know. Which molecule is the most polar? The right one, water. And then, guys, CH3OH has a mid polarity. Is that okay? All right, so now, guys, with the next 20 minutes, let's talk about so what. Here's what we know. We know that CH4 is not polar. We know that CH3OH is kind of polar. And we know that water is really polar. Get the idea? So now, guys, the question becomes this. So what? How does that change the behavior of these substances when they get together in big groups? Well, guys, don't write this down until I tell you, but we're going to pick these off one at a time. What does this do in big groups? What does this do in big groups? Well, we'll go in order. What does this do in big groups? And what does that do in big groups? So, guys, let's do CH4 first. Here we go. So don't write this down until I tell you, but here's the idea. So, guys, all of these are CH4 molecules. What is the polarity of CH4? 0. So what will be the intermolecular forces between these? There aren't any. Guys, if these molecules are not polar, then these things won't attract. In the same way that pens are not magnets. If these are not magnetic, they don't attract. Well, these are not polar, so they also don't attract. So here's the idea, guys. When these molecules come together, if they don't attract, what are they going to do? Fly apart. There's no attractive forces between these molecules, and they just fly apart. Let me show you if you don't understand what I'm talking about. Because, guys, that's what's happening right now. I am now releasing into this room large groups of CH4 molecules. Can you see them flying out of here? Because, guys, guess what CH4 is? Natural gas. And, guys, these CH4 molecules are coming out of here, and they're just flying all over the room. Why don't they stick together? Why don't they stick together? Because they're not polar. And guys, because they are not polar, they don't stick together. And because they don't stick together, what phase are they in? Solid, liquid, or gas? Gas, good. So guys, that is what you need to write down. The idea is this. If you've got molecules that have no polarity, therefore, look at the triple dots. Guys, therefore, what will be the strength of their intermolecular forces? 0. They have no intermolecular forces. And guys, if they have no intermolecular forces, therefore, what phase will they be in? Gases. And guys, that goes in both directions. Anything that you know to be a gas, including the oxygen that we breathe, including the carbon dioxide that comes out the tailpipes of our cars. Guys, any substance that is a gas, the molecules are nonpolar. They're symmetrical. Guys, it goes both ways. So nonpolar molecules are gases, and gases are nonpolar molecules. You get the idea? So let's keep going. Guys, don't write until I tell you. Now let's take a look at CH3OH. So guys, now we're going to get together groups of CH3OH molecules. Are these molecules polar? Little bit, right? Not as polar as water, but they're a little polar. So will they attract? And they will attract positive dipole to negative dipole. And when they attract, they stick together. What do we call those forces? Intermolecular forces. And the intermolecular forces stick them together so they're not a gas. What are they going to be? A liquid. Guys, that's this. There is no water inside this jar. This is not water. There is no water inside of here. For some of you, that's mind-boggling because in your world, everything that's a liquid is water. Guys, this is not water. There is no water inside this flask. This is only these molecules. By the way, the name of this is methanol. This is actually an alcohol. It's wood alcohol. You drink it and go blind. But guys, this is what is called methanol. And the only thing in here are these molecules. And guys, why is this a liquid? Why is this a liquid? Because this is polar. So let's write that down. So guys, the connection goes like this. This is a polar molecule. Therefore, does it have intermolecular forces? Yes. And because it has intermolecular forces, it is a liquid. So what do you now know about all substances that are liquids? Their molecules are polar. So now guys, let's do H2O. You obviously already understand this one. I'll show you just for fun. So guys, here's what molecules. Are they polar? Yep. Do they stick together? Yep. And they form a liquid. This is it. This is just distilled water. But guys, you don't need to write it down again because you already understand that polar molecules have intermolecular forces and those are liquids. So now we're done. And what did we forget to talk about? Solids. So guys, what about solids? If something is a solid, what's got to be true of its intermolecular forces? Even stronger. And if the intermolecular forces are even stronger, what's got to be true of its polarity? Even more polar. Guys, we're not going to show you an example of that, but understand it's true. If you've got substances that are solids, they are even stronger IMFs, so they're even more polar molecules. But we're going to stop there, guys, because now we're going to move into volatility, boiling point, adhesion, and cohesion. And to discuss those, what we need are liquids, because these are properties of liquids. So I just stopped there so we have a couple liquids to play with. Ready to move on? So guys, remind yourselves what volatility means. Go back and look in your notes if you need. So volatility means can it evaporate? So guys, does water evaporate? Sure. Does methanol evaporate? Yeah. But here's the thing that's interesting. They don't evaporate with the same rate. So let me show you what we're talking about. Don't write this down. But guys, here's the idea. If you could look inside either one of these jars, these golden shaped balls could either be the waters or the methanols, doesn't matter. Guys, this is what you would see inside of here. You would see molecules sitting on top of the surface being pulled down by the molecules that are beneath them. And guys, that's what these arrows represent, is the pull. Now, what do those arrows actually represent? Intermolecular forces. Now, in order for then a molecule to evaporate, it's got to jump off the surface. So that's what happens when something evaporates, is these molecules jump off the surface and they leave. But guys, in order to jump off of the surface, what has to happen to these intermolecular forces? In order for this guy to go, what has to happen? These have got to break. Do you get it? Now guys, here's the trick. What do you know about the strengths of intermolecular forces? Well, they're not the same. So water and methanol, which molecule is more polar? Water. So which substance will have stronger intermolecular forces? Water. So which substance will be harder to break apart? Water. So what will that do to water's ability to evaporate? Not as much. Does that make sense? Guys, methanol is less polar. So what about its intermolecular forces? Weaker. So what about its ability to evaporate? Higher. And guys, I can show you that. I'll just do this right now. So I will put water here. So I'm going to spill some water. And then guys, I'll spill a similar amount of methanol right over here. And then we'll speed this up a little bit by spreading them out. Because I don't know if you can see this or not. We'll come back to it. But you can actually see the methanol evaporating. I wish you could all come up here, but you can actually just stand here and you can watch the puddles disappear. Yeah, this methanol is evaporating like crazy. Guys, before we're done with the day, this will be completely dry. But I'm going to have to wipe this up before second period because this water will not be gone before the end of the day. So why does methanol evaporate so much more quickly? Good, it's less polar. So guys, let's write down that relationship. So the idea goes like this. If we have molecules that have high polarities, notice the up arrow. So if you have, so water has a high polarity. Therefore, what will be true of its intermolecular forces? Strong or weak? Strong. And guys, if these intermolecular forces are strong, what's going to be true of its ability to evaporate? Will it evaporate very well? No. Low volatility. But guess what? The opposite is also true. Now let's talk about methanol. Methanol has low polarity. So what's going to be true of its intermolecular forces? Low. So what's going to be true of its ability to evaporate? High. You see how that's an inverse relationship? Strong intermolecular forces, low evaporation, low intermolecular forces, strong evaporation. And it all ties back to polarity. You guys good? We got 2 more to go. Can we go on to boiling point? Kate, are you starting to see how this ties into the question that you ask about? Yeah, this is what you're going to be doing in lab next time. So guys, let's go on to boiling point. You just stretching, Zach? Okay. So guys, let's now talk about boiling point. Go back and look in your notes if you don't remember, what is boiling point? So guys, boiling point is the temperature at which the molecules can all jump out of the beaker. So going back to our picture, this is the same picture as evaporation, right? So what is the difference between evaporating and boiling? And guys, here's the answer. When evaporation takes place, a few of the molecules have enough energy to break the intermolecular forces and leave. What happens when boiling takes place? They all have enough energy to leave. And all they're waiting is for their turn to get to the top. So when you heat something up to its boiling temperature, all the molecules have enough energy to leave, and when they get to the top, they leave and never come back. That's the difference between boiling and evaporating. But now, guys, let's talk. Imagine that this was water. If this is water, what do you know about the strengths of those forces? Are they weak or strong? Strong. And if they're strong, they're going to be hard to break. And if they're hard to break, what are you going to have to do to the water to get it to boil? Heat it to a really high temperature. Do you guys know what temperature you have to heat water to get it to boil in Celsius? Celsius. 100 degrees. So guys, let's write that down then. The idea is this. Highly polar molecules have strong intermolecular forces. Strong intermolecular forces are hard to break. So what's going to be true of the boiling temperature? High or low? High. But now, guys, what about methanol? Let's talk about methanol. What do you know about the polarity of methanol compared to water? Lower. So what do you know about the intermolecular forces? Weaker. So what are you going to have to do to boil this? Not as much. So guys, the other is true as well. Low polarities, low intermolecular forces, that should say boiling point. That's weird. Here we go. Low boiling points. And guys, these aren't numbers you need to know, but let me show this to you. Again, what temperature does water boil at in Celsius? 100. Now guys, if methanol has weaker intermolecular forces, what should its boiling point be? Higher or lower? It's actually 65 degrees Celsius. You only have to heat methanol to 65 degrees to get it to boil. Kind of interesting. Why? Because the molecules are less polar. You guys good? We got 2 more to do and we're done. We're just about there. Adhesion and cohesion, and we'll call it a day. Can we go on? All right. So guys, adhesion and cohesion. Here we go. So first of all, how are you going to know the difference between adhesion and cohesion? Can I give you a clue? Think about this. Think about glue. We all know that glue is an adhesive, right? So what does glue do? Sticks 2 different things together. So adhesion is between 2 different things. And if that's true, cohesion is within the same thing. See the difference? So if you can remember glue, you got it. So guys, I'm going to give you some examples of adhesion and cohesion. Let me turn out the lights so you can see the pictures. So guys, this is one of the 2. Look familiar? Can you see it? Can you see what we're looking at? So guys, this tube is a graduated cylinder, and there's water in it. And what do we call the dip in the surface of the water? Meniscus. We learned about that in September. Why does water form a meniscus? Well, guys, the answer is intermolecular forces. Here's what's going on. If we zoom in to the edge of the meniscus, you've got these water molecules that should be red and white. They screwed up the colors. But you've got these water molecules, and they are polar. Well, guess what? Glass molecules are polar as well. How do we know? Because they're a solid. And so, guys, these glass molecules are polar. The water molecules are polar. The water is attracted to the glass, and it gets pulled up the side. That's the meniscus. Now, guys, what would happen if we put methanol in a graduated cylinder? Would the meniscus be taller or shorter? Shorter, because it's less polar. Get the idea? So that's what causes the meniscus. Now, guys, here's the question. Is that an example of adhesion or cohesion? It's adhesion. It is two different substances being attracted together. So guys, now let's talk about cohesion. What is cohesion? The same substance being attracted to itself. And guys, here's an example. Isn't that peaceful? It's a leaf. But where is the leaf? It's on the water. But guys, it's on the top of the water. But guess what? It's not floating. Guys, leaves do not float in water. Leaves are more dense than water, and they should sink. So why is this leaf on top of the water if it's not floating in the water? Exactly, that's the name of it. It's actually called surface tension. Guys, what's happening is these polar water molecules are attracted to each other, and it creates a skin on top of the water, and the leaf is actually resting on that skin. It is not floating in the water, it is sitting on the skin that we call surface tension. And guys, surface tension is caused by intermolecular forces. So what would happen if we tried to float a leaf in methanol? It would sink because methanol is less polar, so its surface tension is less and it can't support the leaf and it would sink. Good thing our lakes aren't made of alcohol. So, guys, this would be an example of what? Adhesion or cohesion? This is cohesion. So guys, what then is the relationship? Well guys, it goes like this. Polar molecules, strong intermolecular forces, strong adhesive and cohesive forces. Nonpolar molecules, weaker intermolecular forces, weaker adhesive and cohesive forces. So guys, does anybody need a copy of the homework packet? I'm assuming not, because you all recorded homework scores, which tells me you could have printed it off our website. Does anyone need one? You're all okay? Okay. Oh, by the way, guys, I don't know if you can see this. The methanol's gone and the water's still there. Okay, guys, let's go to page 2 and let's talk about the homework. Oh my gosh, arrows. We've been doing arrows all day. Now guys, you get to do the arrows. So let's do the first two together. First of all, number 1. The up arrow means strong. So we have a high boiling point. So guys, if we have a high boiling point, will the intermolecular forces be weak or strong? Strong, so draw an up arrow by IMFs. And guys, if we've got strong IMFs, will those be high or low polarity molecules? Draw an up arrow for high. Now guys, what about the next one? If we've got low polarity, what will be true of the IMFs? Low, draw a down arrow. If we've got low IMFs, what will be true of the boiling point? Low, you get the idea? Okay, now guys, turn to page 2. This is challenging. Here's what it says. For each of the following compounds, draw the Lewis dot structures and indicate the molecular polarity. That was the last homework assignment. But now look at what it says to do. Then circle the more polar molecule. Guys, don't worry about the brief explanation. You don't need to do that. Just circle the more polar molecule. So guys, how do we know which molecule is more polar? Well guys, I wonder if I can do this. I have no idea, but let's see if we can do this. How do we know which molecule is more polar? Take a look at this. Oh, nope. Sorry. I don't know if I can do this. Okay, let's see if this works. Guys, how did we figure out that water is more polar than methanol? Yeah, we subtracted. Oh, it's right there. Guys, remember what we did is we subtracted. We found the electronegativity differences between the atoms in the polar bonds, and the one with the greatest difference was the strongest, was the most polar molecule. That's what you're doing here, okay? And all you're going to do then is circle the more polar molecule from those sets of two. Then, guys, when you turn the page again, this is where the rubber hits the road. So on page 3, it says, regarding the molecules that you just drew, answer the following questions, including a brief description of your reasoning, which should require therefore dots. So number 1, regarding set 1, which will have the strongest cohesive forces? So this is the reasoning. If it has strong cohesive forces, what's got to be true of its IMFs, high or low? High, strong. If it's got strong IMFs, will it be the more or the less polar molecule? The more polar. So you're going to go back to set number 1 over here, and whichever one that you circled is the most polar will be the answer to number 1 back here, because high polarity, high IMFs, high cohesive forces. You get the idea? All right. So guys, you have got 12-ish minutes to work on this. Let's dig in. We'll grade this on Tuesday. Actually, we'll do a lab on Tuesday, but then, guys, we're going to spend all day Thursday also on the lab. So you'll see. You're leaving, right? Oh, you're leaving. Oh, yeah. Oh, yeah. Here. Oh, yeah, for sure. All right, guys, go get them.